Hi, Year 11. Today we're going to look at using the idea of collision theory to explain changes in rate of reaction. We've got a bit of a definition here. So it says that collision theory, chemical reactions can only occur when reacting particles collide with each other and with sufficient energy. It also states that the minimum amount of energy that particles must have to react is called the activation energy. So if we have a look on the right hand side here at this diagram, we have two particles. It could be atoms, they could be molecules. They collide together, but they don't collide together with enough energy to react and form new substances. So these did not have the activation and they didn't have enough energy. Just below we have a successful reaction. So these have collided in exactly the same way as these two, but they've collided with enough energy to react and they've formed two new products. It's a little bit difficult to see in black and white, but these are different to our initial particles. It's illustrated a little bit better on the diagram down here. So we have carbon monoxide colliding with an O2 molecule, and that forms carbon dioxides and oxygen over here. So we have a successful reaction happening there. We need to use this idea of successful collisions to explain the effect of four different factors on the rate of reaction. So those four things that can affect the rate of reaction are temperature, concentration or pressure, and these are kind of the same idea. We'll look at those again in a second. Surface area and catalyst. So the use of a catalyst is a little bit different, and again we'll talk about that in a second. We'll start off with temperature. So if we increase the temperature of a system, the particles have a greater kinetic energy. So, and if they've got greater kinetic energy, this means they're moving faster. So our particles are now moving faster. If they're moving faster, then they're more likely to collide with each other. So we can say that there are more frequent collisions. Now we have to be a little bit careful with our language here. We can't just get away with saying more collisions because we're looking at how fast it happens. Over the course of the whole reaction, we'd probably have the same number of collisions regardless of the rate, but we're looking at it per second, so we have more collisions per second. We need to mention that idea of frequency. So we have more collisions happening per second. We also know that the particles are moving faster, so the particles have more energy. And if they've got more energy, then there's more chance of a successful collision. So there's more chance of the particles having the activation energy. So let's try and just fit this in with more successful collisions. And because we've got more frequent collisions, we've got more successful collisions because the particles have got more energy, we can say that the rate of reaction is going to increase. Now the converse is also going to be true for all of these. So if we were to decrease the temperature, the particles would have less kinetic energy, they would move more slowly, we'd have less frequent collisions, the particles will have less energy, so there will be fewer successful collisions, and hence the rate of reaction will decrease. If we move on to the next category, we have concentration and pressure. So concentration and pressure are both a measure of the number of particles per unit volume. So if we increase concentration, we're putting more particles, more mass of dissolved substance into a set volume of liquid. If we're increasing pressure, usually we're talking about gases. That means we're pushing more particles into the same unit volume. The effect this has on the collisions is we have more frequent collisions, and again I'm using the idea of frequency rather than just number of collisions, as there are have more particles per unit volume. So more particles per unit volume. And just note, I'm being very precise with my language here. If we move on to the effect of the energy, effect on energy of the collisions, well, we could increase the concentration, we're increasing the pressure. This doesn't really have any effect on the energy of collisions. We're not making the particles move faster, so it has no effect on the energy of collisions. I say this will also increase the rate. So what I hope you see is that every time you get asked a question about one of these factors, we have to comment on the frequency of collisions and the energy of the collisions, and we have to say what it's going to do with rate. The next one is surface area. So this is kind of the idea of, it's the difference between having lumps of something and maybe grinding it up into a really fine powder. In both instances, we've got the same volume of reactant, the same volume of solid, but if we grind it down into a powder, there's a much greater surface area, so the particles can access a much greater amount of the substance that's reacting. All we need to be able to say though is that increasing the surface area gives you more frequent collisions. So we don't need to know too much about this, we just need to say it's more frequent collisions. And just in the same way that concentration and pressure had no effect on the energy of collisions, neither does the surface area. So here we say no effect. But because we've got more frequent collisions, there's more chance of a reaction taking place, so the rate of reaction will increase. And just underneath we have this last idea. So we're looking at the use of a catalyst. So a catalyst is something that speeds up the rate of reaction without being used up itself. So it kind of doesn't really take part in the reaction. What it does do is provide a different pathway for the reaction that has a lower activation energy. So the particles can collide with less energy than they could previously and still react. So catalysts will increase the rate of reaction. They don't affect the frequency of collisions, they don't affect the energy per collision, but there's more chance of a successful collision because it needs less activation energy.